Hallo, sag mal Hallo. Trägst du vor? Euer Paper? Nee. Okay. Okay. Okay, gut. Okay. Okay. Now people are coming. Okay. Maybe we should wait one more minute.
Just a synthesizer that we are doing with. It's basically it started as a node-lit, and now it's going to. No, it's a personal project.
Okay, take your seat. I was told we have a very tight schedule today, so we can't wait too long. And so, yeah, welcome to paper session 5. We have 4 papers in this session. And if we can all... Okay, so the first paper is presented by Luca Richelli, and it's called Inside Andrea Molino's La Vérité par toute, the creation of swarm sounds. Please.
Thank you. And thank you for all for being here for this presentation. The title is what they saw here. And there was a composition of Andrea Molino that was made 2 years ago in Accademia Chigiana. It was a large opera, we can say a huge, for our opportunity. And there was involved many person, one of which was I, myself, and for many reasons I have to present the technical part of this work. And so I start to just recap what is La Vérité par toute is a last card word for Andrea Molino. It's score for many voices, 8 percussionists, and 16 mobile video cameras, fixed media, and live electronics. So, what is typical of this piece of composition? It was a piece just think for a particular place. This is the church of Sant'Agostino in Siena, and because all the scenography was thinking about this beautiful place, and I have to show you later. In all of this world, we focus on the digital creation of a sonic swarm. So this is the main view, and we saw all just a little bit of all this part. And this is the sonic creation of the fragment of flying in space, because this was one of the idea of the composer to have this swarm just flying in the space, and there was really something challenging to recreate from a phonetic material what the composer wants. And so you can see the inside of the church, and this was the sketch of the idea of the composer to have something round in the audience. And maybe you can see the percussionists are all around the stage, and the public is inside, and the director just in the middle, with all the singer in many positions changing during the piece. And with all this moving person and the 16 mobile camera. There was other people to dynamic mic, so it was really a mess to make the rehearsal of all this piece. We have to simulate this swarm of sound. Of sound, or we can say of phonetic sound, because maybe if I just time I can show you just a little bit of the part, but all start from the decision of the composer to compose the swarm 2. So we have about 800 little fragments of many paraphonetic voices, or pre-recording in a soundproof booth to have all this kind of sound. And of course, the swarming sound technique is not something new. There was in the literature many way to approach this kind of thing. One is algorithmic composition, so particle system, Boyd, or automata. The other way could be time granulation of the sound grain, or use spatial audio, ambisonic, binaural, or other thing to just have the movement of all this sound. AI machine learning, but we have to put many things inside, and so we don't use this at all. And interactive system, we can say we use a hybrid approach. So something is synthesis, but the most is field recording. It's not field in the sense of we go outside. Instead, we are pre-recording with the choir all what we need. So at the end, we use about 1, 2, and 6 separate things to achieve what we want. About the technical implementation, it was using a machine running on Debian with vanilla pure data for alter operation with no particular external. We build all and all is down. We can download from GitHub all the project. And how they say, there was this huge database of all this grain with many kind of articulation, and a big work was to label all this kind of sound, because in the score was asking to use something instead of the other. So there was a big work. I didn't make that. That was my good luck. At the end, we decided to use a dynamic system, which up to 256 parallel generator, and this was made dynamic in PD using the script mode, so we can, during the need, to change the number of the voices just on the fly. The only thing we couldn't make during the sound, so we have to change or prepare. I let you show after the PD patch how we can use this system. There is a configuration manager to read the text. There was responsible for how to use and to move all this material. And then we have all the part of this configuration, so the sound folder, the number of parallel swarm, and one type. So we can say we have a parallel text score for the using of all this material during the performance. And we have to random choose all this material with the correlation to have all this idea of swarm sound. And one was the most interesting thing is we arrived with many discussion and about experiment to have this two curve to correlate the amplitude with the density. Because there is something always impossible in the composer question. That was against the acoustic reality. In this case, to Earth in the same way one single fragment to all the fragment, and in reality it's not possible to have the same level from one people to 2,000 level. It's not the same. So we decided to manage in some kind, and then I let you hear what we manage to use this two amplitude equation to have of course, the amplitude go down when the density go up. And I think I just arrived at a good goal because the composer was happy, and that was we are happy too. And you can say the AB linear factor are something you have to decide specific in every place, because the correlation respond on the acoustic of the audience. So we put in this situation two number, but you have to change and make many rehearsals to have a good fade between one person to all the people murmuring. That was the big challenge of all the world. So to recap, to have the same level from solo to tutti effect compensating the two level. The spatialization was really not complicated, simple. We have 8-channel immersive mode with the round location to have this movement, but was useful to have 4 independent and mono channel for direct movement, to have something really precise in some point, and to make a change between the fade between the input. And there was a mono sum for all this global reverberation, not very much because it was in a big church, so we don't need very much, but it was used for other purpose. So we have at the end 13 the correlate output channel to use for this. We can say up and down between we say the dark matter background, so we can understand nothing. We can say when we are in this situation where we can perceive, we understand we are in a place with or people they are speaking, but we can understand one single fragment, and then we have the possibility to arrive to the point when we can, at the end, focus on one voice. This was another require of the composer, and we just manage with this way to have all together, and then the single, and then move with the control fader. Okay. Not want to go out of time. So, record interface. This is just what I see in advance. So, there was one of the score, not of the piece, but the score of the fragment that was prepared from the composer. And we use about 1 week to record all this material. So with close miking, label, and there was all the thing that was made in advance of the composition. And at the end, this is the simple recording interface, just in PD, and it was controlled by via OSC. With a normal controller with the fader, and you can see the fader. And this is not the amplitude, only the amplitude, but this is what I say in advance, so the correlation between amplitude and density. So I go up with the density and go down with the amplitude. We have all the same level. And so just to recap, this is the 4 potentiometer. This is the bottom. I forgot to say there was many preset to use during the score according to the recording material and then the score that was made and then the OSC control physical surface. So we decided to develop in vanilla to got with this swarm generation, to combine algorithm control with artistic expression, to have the both part of the side, we can say, from one side the control and then the artistic need of the composer. Free software approach ensures sustainable. It's not so easy, we all know, but this is one way. To have something, you can download all the patch from the GitHub, and then you have the address if you are interested, or just email me to give more information about all of this. Just to and in the presentation, this is all the people I have to thanks for all this word, the composer, the academic Jana, all the conductor, the performer, and so on. And okay, this is the end of the presentation. Just to have an idea of the piece, just let you see, this is the church. We can I just crop some many points where I think you don't have, of course, the effect of the swarming voice because there is a stereo, and we don't have the multi-channel, and we don't have to separate all the source. But we can have an idea of what kind of opera was and the situation. Oh, sorry. This was the first part because the piece come direct from a piece from Luciano Berio cycle. So in advance was this piece, and then abruptly there was the starting of La Vérité Patou. And so we have this bridge between the two opera. With all this murmur just going in the church. So we can have an idea of what happened. Just another point. And it was used during the changing of the part of the pieces. So we have on the double sound of the real sound of the people they are moving, and the sound of all the this swarm. Okay. and then just to finish, just really easy. That was controlled with the external. So so this is the sample of one swarm. You have some little voice, and then when I go up, of course the volume is not the same, but if you don't make the compensation, even worse, you can use all this dynamic range we have in this way. The use of this is exactly the same because I made a mix of all the 8 channels in a stereo to the conference. Instead, this was originally built for an 8 channel, and these are exactly the same, just to have the idea. Of course, when I am playing, I can change the preset because the script just clear all the patch that was created and then create another one. So, but in the score was not one after the other, but we have many time to rebuild automatically the different swarm type. So just to have an idea, this is another one.
The code, the convent napkin.
Okay, this is the spoken one, and then something different. Maybe this is some more. Another kind of swarm.
Yeah, thanks for the nice presentation. Do we have questions from the audience? Because I might have 1, 2, 3 or something. And we have time. When are how are the swarm? Do you have examples for the swarm movements, and at what moment, or did I get that wrong?
So I didn't catch the answer.
You had the grains moving in swarms.
Yeah.
In ambisonics or in some. Do you have examples? My first question is: at what stage were these movements calculated, or the trajectories?
No, the trajectory was made with orthophonic system, so we can hear them now within a stereo reproduction. So we arranged to move between the loudspeaker, and there was the part made with another computer. They made only the spatialization with the movement. This is only for the swarm sound. So we produce all 8 together, and then or one. With the one, we made the movement.
Okay, so one computer did the swarm, the grains, and the next computer did the spatialization?
Yeah, the spatialization and other things again, because we have this to change between this situation, and because we have to change the preset and then rebuild, we can say, the patch. So we have to start from scratch every time we can the preset, and they should be in one computer. The other computer have to running all the piece long because there was other thing to do, too many DSP effect to take along, and we can give to have in the same machine to have the both process. So we have to split into machine, and the other machine take the sound and make the movement.
So that means we did not see 8 loudspeaker signals in the
Yeah.
patch, but 8 grain streams. And
Yeah,
they were,
exactly,
okay.
exactly.
Anybody else? Before I go on with my questions. Yeah? Yeah, sure.
Yep. So, how much the score is notated? Basically, my question is, do you receive a score in which the composer asks for a swarm sound and you choose by yourself to implement it in a combination of 1 to 6? I mean, with that pattern of way, or the composer suggests you to do something more precise?
No, that was the choice of the composer. We follow all what is in the score notate. So they made all the score for the pre-recording. We make, of course, the recording and the labeling. And then when he told the material, decided in the score, I want this kind of murmuring, preset 1 in this part, and so on. So we are just made for that score. So it's following the score, exactly. Yeah, exactly.
So if we have no more questions, then we can move on to the next speaker.
Thank you again.
Okay, thank you. Yeah, thanks again. So next talk is by Victor Zappi, and it's about Linux audio on Android. Just give him some time to set up. Ich habe hier keine, I don't have any control over lights, but
Hello, everyone. Thanks for the introduction. So let's start it. Android phones. I have a love-hate relationship with them. So they're definitely marvels of engineering, and they have very good audio potential. However, I really dislike developing for them. The problem is the Android stack. Some of you may be familiar with this. So what does it mean? It means that the applications, the apps that we design, they stay here on the top, and they have to comply with a lot of intermediate layers, software layers, which means that the development is more difficult than what is typically is on other embedded platforms. And also, the application is very far from the hardware, so the hardware capabilities, meaning that whatever we design, no matter how hard we try, is inefficient or less efficient at what it could be. And there's a third problem that is incompatibility. Indeed, sometimes Google updates, improves, or simply changes some of the intermediate layers, which means that our code runs the risk of, not running correctly anymore, and we need to patch it. I really dislike this process. And if we look into Android more closely, we understand that it doesn't have to go this way necessarily. In fact, every Android version is branched from a stable Linux kernel version, which means that they're basically kind of the same thing. The branching, of course, introduces some modifications, but somewhere here down the line, these branches started including also the ALSA subsystem, meaning that theoretically, it should be possible to design audio applications at low level on Android phones, much like what we do on embedded audio platforms, like the Raspberry Pi or Bella. So my question is, how can I do that? This is what I wanted to understand. And let me be more precise. I want to code on my computer, build a binary using whatever editor I want, not necessarily Android Studio, and move this tiny binary to my phone, make music with it, and have fun. And beyond the workflow, what I really wanted is something that is low level, something that interfaces directly with the hardware capabilities, specifically the sound card that these phones come equipped with. And I know that there are many reasons, good reasons, for this workflow to be not possible by default. We can talk about privacy, security, but here I'm talking about a completely different scenario. I have this phone, I bought it, I own it, I want to use it however I want it, right? I'm not talking about sharing a device. Heartfelt. I'm not talking about sharing an application through an app store and monetizing. I just want to use my phone in the best way possible. So here comes a project I've been developing with some collaborators over the last 3 years. It's called LDSP. It's an environment that allows, with some caveats, allows for the development of native low-level audio applications on Android phones. The idea is to create an environment that allows us to use C++ and also pure data, to be fair, in the same way we do on embedded audio platforms. And it's based on 3 pillars: ease of use, optimization, meaning that the binary is actually optimized, it works as fast as possible, and of course is open source. Indeed, you are more than welcome, actually kind of encouraged to peek at the source code on GitHub, and you can download it, and by the end of this presentation, probably you will have a better understanding of how it works, and if it's something that you may want to try on your own. So let me explain how the rest of the presentation is laid out. I'm going to start by describing generically how we can develop low-level C++ applications on Android with a specific focus on audio. Then I'm going to talk a little bit more about LDSP and its components. And finally, I'm going to share with you briefly some technical and philosophical motivations behind this work. So let's start from the first part, low-level C++ development. What do we need? I'm going to start from the Linux paradigm you're pretty familiar with, and then switch to the Android one, with underlining the differences. We need a tool chain, right? A tool chain, by definition, is a combination of tools. We need a cross-compiler, a linker, system libraries that match the architecture we are targeting, and hopefully some debugging tools. Unfortunately, we cannot use a generic ARM cross-compiler or toolchain on Android for a variety of reasons, deriving from the fact that the Linux version that is used on Android is different than the one that we use on embedded platforms. Luckily, to generate this bin, this ELF bin, what we really need is just the Android NDK, the native development kit that Google designed so that people can embed native C++ components into apps, but we can use it just to build a binary if we use it, kind of in a hacky way. Once we have that, of course, we need some dependencies, CMake and Ninja. These are readily available, so no big deal. But once we have that ready on our computer, we can use the NDK with whatever editor we want, and it's time to deploy the binary on the phone. Deploy, of course, means pushing the binary to the phone, but also run, stop, and debug it, which calls for some extra tools. There's no SSH on Android Secure Shell, but again, Google designed something that works kind of in the same way. It's called the Android Debug Bridge, or ADB in short, and coupled with some shell scripts, we can push the binary and basically run, stop it, debug it, and get some console feedback on our computer, basically closing the development loop. So easy peasy. We can use tools that exist already to develop a binary at low level. But if this binary is audio-oriented, at a certain point, it will have to access one of the audio device nodes that the driver exposes in the file system. And unfortunately, the Android shell user, the default one, doesn't have permissions to open these ALSA devices. So the trick is to run the binary as root. And if you're asking, no, there's no audio group On Android, unfortunately, root is probably the best solution. And rooting means that we need to root the phone. We need to install the SU binary in the system. And this gives us, of course, access to the audio driver, but also gives us some extra pros, like real-time priority for the executable. We can control the frequency scaling of the CPU, and we have access to all the other kernel subsystems, including the input events, touchscreen, and whatever sensors our phone is equipped with. So we have full control over the hardware, finally. Now, there's another hoop we have to jump through. That is the mixer. Because every phone comes with a codec, so a DAC and ADC, that has a mixer. This is kind of the same that we see in embedded audio platforms, but the mixer works in a slightly different way. In the case of embedded Linux, the mixer is abstracted into a device tree. What it means is that, of course, the mixer needs some specific commands or controls that are tied to the hardware, the brand, the model of the mixer. But these are in the device tree, meaning that any generic user request is pushed to the driver, and the driver has the onus of translating this generic request into specific ones. And unfortunately, this is not the case on Android. And by the way, if you're wondering what does the mixer do, well, it simply routes whatever, in the case of playback, whatever audio streams come from the active device to the different physical destinations, including speaker, headphones, and headset. So how do we do this? How do we route these streams in Android if there is no device tree from audio? Well, vendors like Samsung or Xiaomi, they typically include an XML file somewhere in the file system that includes all the controls, the specific controls for the hardware. So we need to find that, first of all. And then, once we find it, we have to understand which controls may activate, for example, this path or this path here. Unfortunately, a single control is typically not enough to activate a path. We also have to control some levels, activate some switches. But luckily, this XML file is arranged into elements, like these ones. And these elements basically include all the controls to activate the different paths. And they have names that basically underline which paths will activate. So we need to find those path names. So going back to the example before, if I want to activate this specific one, I need to look for the one that is called, in this case, deep buffer playback. So we look into the XML file, we pick every control inside of that element, we pass it to the mixer through the driver. For this path, same. I look for this specific name, I parse all the controls inside of the XML file, I pass them down to the mixer, and voila, it works. Complicated, but it can be done. So, eventually what we need, the minimal, let's say, minimal requirements to access the mixer and have a fully working audio binary is to know the location of this XML file and the name of the paths that are needed to connect the devices to the destinations or the physical sources like the microphones. Specifically, we need only 2 paths for playback and capture. In the paper, I explain how we can do a trick and use a single one to activate all the different devices. And then we need 3 for playback destinations and 3 for capture sources. And while these are vendor or device dependent, there are some, let's say, common practices that help us hack or sniff this kind of information from the system. All right, so we have all the pieces that we need generically. Let me show you how all this knowledge is compressed into LDSP so that it's readily available for you. Kind of. I mean, there's still a little bit of a hacking configuration needed, but at least you have an environment where you can work safely. So there are several components in LDSP. The first one is a C++ framework that is built around a tiny ALSA audio engine so that we can talk directly to the driver at low level. And then, of course, it includes libraries and examples to make development easier. And unfortunately, it requires to know the mixer paths. So it requires some kind of manual configuration. The second component is an infrastructure of helping tools that have 2 main aims. The first one is to build, deploy, and debug. So these scripts allow us to do this in a kind of seamless way. We need though rooting. We need to be root, as I said earlier. Otherwise, there's no possibility to connect to the audio driver at runtime. And then there is a set of supporting scripts that makes our lives a little bit easier. That they help us understand how many audio devices are available on the phone, where the mixer file can be, and how to extract the path names. And of course, we don't have to forget about the dependencies. Again, it's Android NDK and ADB supplied directly by Google, and CMake and Ninja, which are pretty straightforward. All right, so when everything is combined together and we use this framework on a configured phone, what we obtain is an application that looks like this. So this is the actual stack. Looks silly. Yeah, it's supposed to be like that. We have an application that speaks directly to the audio driver. But if I show you side by side what a regular app typically is on Android, you truly understand the big step that we see here, right? There's a lot of computational power that probably can be redirected into audio that on an app is instead kind of wasted across these so many layers, many of which are closed source, many of which we cannot skip. What about developing? So what a developer is supposed to do to use LDSP? The project comes with an API that is very similar to the one from Bella, if you know it. We just need a single CPP file that implements a setup function, a render function that is basically the audio callback, where you have access to incoming and outgoing audio buffers, and eventually a cleanup function. And this is how a simple mathematical sinusoidal project looks like. This is literally what you need to write if you want to have a 440 Hz sinusoidal blip coming out of your phone. And nothing special again. It's supposed to be like that, right? It's supposed to be as simple as possible. But in many cases, we're using other environments on Android, this is not the case. Also, let me show you a more advanced project. This is a kind of a fully fledged application. It's kind of silly and fun. It's basically a makeshift pedal for guitar. I mean, I think you got the point. It's super simple. And the idea here is that we are using a phone that has been discarded 6-7 years ago. It was there, tucked in a drawer, and it can still be used to do some music, to make some music. It's fun. Of course, there's a little bit of circuitry you can see there, a little bit of circuitry to do some impedance bridging with the actual amplifier, but nothing crazy, like a few euros, a few dollars. Very, very simple. So let's go back to the presentation. This is the code for this specific application. Again, just a few lines of code. In this case, we are using some of the libraries that are available in the environment. Specifically here, we're reading sensors. We're using the accelerometer to basically mimic the, like pushing a pedal. And beyond that, we can access buttons, the multi-touch screen, vibration, even the flashlight. And of course, there are some audio goodies like filters, parallel FFT using the Neon coprocessor that is available on every phone, audio file handling, MIDI, OSC, whatsoever. And in fact, here we can see how easy it is to use one of these libraries, basically instantiate an object and run a process function method on whatever buffer you have, both at control or audio rate. So, is it worth it? Because there's a fair amount of configuration that needs to be done. Yes, it is worth it. You don't have to take my word for granted. We ran a couple of studies. We specifically compared the same C++ code, but dropped in an LDSP environment against dropped in a regular Android app. Optimized one. I want to emphasize that we spent a lot of time to optimize the Android app. And we looked for metrics to understand what kind of performance gain we could find. So let me give you more details about these two user studies. Of course, I'm going to be very brief. You can find these publications. They're both at DAFX, Digital Audio FX Conference. In 2023, we focused on an oscillator bank case, and we counted the number of oscillators and the buffer sizes that the two systems could leverage. And of course, we noticed that LDSP grants a higher oscillator count consistently, as well as lower buffer sizes down to 32 samples, which is pretty nifty for all, especially for all devices. And the year after, we focused on kind of more advanced technology, neural audio processing. Specifically, we designed 3 virtual analog models that are based on black box neural networks. And we ran them on a plethora of phones, from very old ones to new ones. And we tested the inference times, and we noticed that LDSP supports lower and more stable inference times. And smaller buffer sizes, but more importantly, we were able to run the lighter models on very old phones. The same models on old phones, but through an app, could not run. So this was a big win. We were very happy about this. And again, if you're interested about all the details and a more in-depth analysis of the results, you're more than welcome to access those papers. So, beyond that, beyond the technique, right, beyond the more technical side of things, I'd like to add a couple of words here. This is all fun, it pays off, but I want to talk a little bit about kind of philosophical approach behind this project. Of course, in the paper, I delve much more into this, so here I will be extremely brief. You may be familiar with the concept of hacking a tool, right? But this is not what we're seeing here. The kind of approach that we tried to take is hacking a system, the whole Android ecosystem. We're trying to use not just the phone and its operating system, but also all the tools that Google provides us with to basically reverse engineer it, sniff information, and try to make it as open as possible. And these are some kind of, I would say, social and sometimes political implications. So what we're trying to do is to basically brush off some of the negative connotations that mobile development typically has nowadays. I can throw at you some words like market, which is fine, but also closed source, standardize, sandbox, and some nasty stuff like data privacy, data brokers, and stuff like that. What we want to do is to actually use this project to hack the system and enter a domain where we're talking about rapid prototyping, DIY, but also open software, open hardware, and communities. We want more people to be able to use phones the way they want. Self-sufficiency, build and democratize low-level applications beyond social, cultural, geopolitical borders, and also monetary constraints. Sometimes we have a phone, it works, and we can make music with it, low level, but no, because Google decides that we can't, right? So maybe this is a good way to bend the rules and have fun with it. And then let me conclude with a glimpse at the roadmap, just one single entry regarding future work. Of course, we have this, I forgot this, sorry. We have this environmental issue, and part of the e-waste nowadays that we generate comes from phones. So this is not a solution. LDSP is not a solution, but it's a sustainable alternative to upcycle phones into something useful. And again, back to the roadmap. One of the reviewers, who I thank, even if I know the name, I don't know the name, said that, yes, this is Linux audio, but not necessarily Linux audio on Android. And so we're trying to kind of close this gap. The idea now is to design an LDSP version, kind of a library that can take the place of the Oboe audio library that Android develops and ships, so that it can be plugged in there inside of an app, and at that point we can really use Linux audio and its pipeline to on Android apps and communicate it directly with the ALSA driver. So stay tuned if you're interested into kind of a hybrid approach in which you still have your regular app ecosystem, but under the hood it speaks directly with the ALSA driver. And I conclude by saying thank you to all of you, but also to all my students, collaborators that work on different modules. Probably the architecture overall of the project is not as stable as I learned today in one of the previous presentations, but we're doing our best to make everything open source, so we try to get as much feedback as possible. And also we have a hands-on workshop today at 4, right after the break. You don't need a phone. I have with me 10 phones, so you just need a computer. If you want to have fun with C++ low-level audio on Android, please come meet me here during the break. Thank you.
Yeah, thank you, Victor. Do we have questions? Okay, and we have some time. Okay, let's just start in the back. Yeah.
Actually, I have 2 questions. First one, if you connect your application to, for example, the speaker via these mixer controls, can you prevent Android from messing that up from changing it?
So you're asking if I decide a route, an output route, I can prevent Android from deciding the correct one, right?
Yeah,
yes,
to change
absolutely.
it. Okay.
Absolutely, yes. Yeah. This is working so low level that Android has no idea what's going on.
Okay. Okay, second question. There are these Linux apps which you can have from Android. So there's an app which gives you a Linux shell, basically.
Oh, yeah.
And maybe other applications like Python or whatever. Can you use your system from that context?
So I think you're referring to Termux. There is a self-contained environment that is basically contains all the Linux, most of the Linux command line binaries. Yes, you can use that if you want. Yeah, this is an extra step, but if you have that, yes, you can definitely use SSH. You can use your generic commands that you use in your usual pipeline. Yes, we just try to rely on whatever is available by default, because no matter what, you need to root the phone, you need to do some configuration, you need to download the NDK, and the ADK also comes with, not necessarily with, but the platform tools that Google provides come with this ADB, so it's very convenient. But yes, if you prefer to use...
The idea was really to do it without having any Android stuff in between. So you start in an Android app and you do everything from there. That's the background of my question.
So, sorry, can you repeat that?
So you do all the development in the Linux environment, which is already an Android app. Then do you still need the Android tools to do that?
Yeah, so yes, there's, if I understand correctly the question, you're saying if it is possible at that point to remove completely the dependency on those specific Android tools.
Yes.
Unfortunately, the tool chain, I mean, you could recreate potentially a tool chain from scratch. You could configure your tool chain and to match the file system, the system libraries that are on the phone. It is possible. It takes a fair amount of time, but if anyone here has the time to work with me on this, happy to do so. Yeah, there is the possibility to have a completely, let's say, Google-free approach. Yeah, potentially, yes.
Thank you.
Hi. First off, thank you very much for working on this. This looks so nice. I'm just kind of scared to root my phone. Like I heard there was security concerns, right?
So rooting the phone, that's a different story, right? So it's a requirement, but it's not something we provide advice on. It's really phone-specific and vendor-specific. What I typically say, and it's written in the paper too, there are some communities online that explain exactly what you can and what you can't do on your phone, given the model and the vendor. It's called XDA developers or XDA forums. And it can be a little bit dangerous sometimes, depending on the model. Sometimes it's straightforward, sometimes it's a little dangerous, and sometimes it's not possible at all. So there's a variety of options.
Okay, thank you.
But once you do that, there are ways to make the phone work as if it's not rooted. So banking apps, double-factor authentication apps, all this stuff works on my phone, and yeah, I just had to flip some switches.
Perfect.
The mixer paths that you're getting from the XML configuration file, you said you're passing those directly to the driver. So are they like PCM names, or are they like use case manager, use case names? What are the mixer paths exactly?
The mixer paths?
Yeah, yeah.
So it's something that is activated. So what are the mixer paths? They are literally connections between inputs and outputs in the mixer that stays on the codec, that lives on the codec. And you send these control messages. You say, activate this specific part of the hardware, deactivate this switch, activate this switch. So it happens at a very hardware level.
And you do that by talking directly to the ALSA driver.
Say that again?
You do that by talking directly to the ALSA driver.
Yeah, so inside of the ALSA driver, there are some mixer utilities that typically are used by closed source parts of Android. But what we did basically was reversing engineering that. It's pretty straightforward, actually. And send through tiny ALSA, which is a user space interface, send those commands down through the driver directly to the mixer.
Okay. Are these, I'm just curious, are these Android-specific extensions to ALSA, or are they on normal vanilla Linux?
That I don't know. It will be very interesting. It's something that I've always asked myself, because there is a mixer even on my computer, right? So it would be interesting to see if the driver is different, or these are basically generic mixer utilities that are available in the ALSA driver at kernel level.
Hey, very nice talk, thanks. It's been a while I hacked on ALSA devices, so I wonder, does ALSA on Android support the fancy Bluetooth headsets and also this 3.5 millimeter USB, adapter, because modern phones don't have this output anymore?
Good question.
Work on ALSA?
Good question. So what does the ALSA driver support? The ALSA driver is what is running even when Android is running, right? So whatever is supported by the phone goes through ALSA since Android 2.3. So yes, everything is supported, but there is a but. For what concerns the adapters, USB adapters, yes, no problem. This is read as an external card, an external USB interface. You just switch a flag, say instead of using card 0, which is the embedded one, use card 1, and you're good to go. For what concerns the Wi-Fi, the Bluetooth, and even the voice calls, well, those are different pieces of the codec. They need different drivers, and I never looked into those. So while potentially the driver definitely can support those streams, the activation is something that I never reverse engineered because it lives in a different part of the hardware. It has different, they are called hardware Android layers, these little libraries that vendors design.
Thanks.
Yeah, we can take one more question. Yeah.
You're Patrick. Yeah, nice to meet you.
Hello? Yeah. Yeah, no, I'm just saying if you're interested on, like, for example, how that USB digital audio headsets and the Bluetooth, how that works, you can come to and talk to me because I'm pretty much the one that worked on it. And as a matter of fact, all those mixer control that Victor showed, actually started by me back in 2010.
Whoa!
So, yeah.
Thank you again. Yeah, I thought there would be some more discussion on this one. So next we have Bill Gribble. There he is. And he's going to present MFP, a graphical patcher extensible in Python and Faust.
Oh, it does work? Oh, okay, perfect. Hello, check, 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 check. Can you hear me? Hello, 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 hello. 1, 2, 3, 4. There's a... No. 1, 2, 3, 4. 1, 2. Okay, awesome. Okay. Slideshow. Great, there we go. Hello, everyone. I'm Bill Gribble. I'm going to be talking about MFP, my project. I'm a unaffiliated software developer. MFP is a graphical patcher I've been working on for some years. I presented the first release version of it at LAC in 2013. I haven't worked on it continuously since that time, but it's been around for a little while. So I decided on short notice to change the focus of this talk to be mostly a live demo, but I'm going to jump around in the slides. This QR goes to the Google Slides deck, and actually the speaker notes on the slides have the remarks I was intending to deliver, so I probably won't get to all the slides since I'm focusing on a demo, but feel free to read through the talk that I would have given. Okay, so I'm just going to jump right into the demo. Can we see this? Yes. Okay, so what is MFP? Just from looking at this, it's obviously a patcher. If you've seen Max or Pure Data, it's going to be kind of familiar. A little tour of what the app is. There's this canvas area where you can edit patches. There's down at the bottom here, there's a status line, which is also kind of a command line, Vim style. Right now it's showing the current input mode on the left and some information about the current rendering rate and DSP information on the right. There's a sort of attribute editor panel over here on the right side, which is it lets you view and edit properties of the current selection. There is there's a log window down at the bottom that shows timestamp status messages and prints and stuff like that. Behind the log window, there's a redeveloped print loop, which you can use for debugging and data exploration. So what does this patch do? We can look at it. It should be pretty legible for anybody who's familiar with PD or Max. We have this number box that's set with a comment BPM, so I would guess this is a BPM value. It's converted to milliseconds and fed into a metro object, so we can assume that this is a clock. It has a button labeled start, a button labeled stop, so these are controls for the clock. And those, the outputs of the metro goes to this circle here, which is, in MFP I call these vias, sort of after the printed circuit board like technology idea. A via on a printed circuit board is like a drilled conductive hole that goes between layers of a printed circuit board. It's like a wire that's invisible, so it's like the send receive objects on PD. And but it also ties into this idea that MFP patches are organized in layers, which are equivalent in some ways to PD's subpatches. So they're just ways of kind of visually organizing related elements in the patch and kind of separating them from one another. Up here in the top bar of this tile, we see the word clock. So that's actually the name of this layer. If we go to the layer menu, we can see that there are other layers here as well. So they're going to be making use of that clock. If I go to one of them, zoom out a little bit. So this is a sample player with like a simple 16-step sequencer. If I'm lucky, I can click this and it will make a noise. So I plugged in the audio out here. No signal. Let me make sure. So I am. Oh, it's my fault. As usual, the volume is down. Okay, now let's see what I did. Okay, right. So this is a step sequencer that's going to use a clock, so we can put in, a pattern of, beats here, something like, I don't know, I like this one, maybe like that. So now when I start the clock, it's going to play something. I'll jump back up to the clock layer and click start. Okay, right? Similarly, we have other layers. There's another sample player that's playing a hi-hat sample. It's also got a 16-step sequencer. I'm just going to kind of put on some not really controlling the pattern here, but usually works out with a hat. Okay, sounds all right. And of course we have a snare, another sample player. So again, these are just 3 layers that implement kind of similar similar patches. I don't want that there. I want that like there and there. All right. So this is not that complicated, but I think it shows a few things about what's going on here. There's a lot of similarities to a PD patch or max patch. The key thing with playing samples is this object called buffer tilde, which actually has a lot of sophistication. It can be used to record, playback, loop, and loop audio signals, but right now it's just loaded using libsound file from a file on disk, and it's just sticking in the buffer. So we can get something else going here. Okay, let's see. So this is, on the left, there's a table widget. This is kind of like iTable. It stores an array of values that you can click and drag to change them. Right now, they're all zeros. And this is like a simple Karplus-Strong synthesizer that has a Faust. It uses like a Faust Karplus-Strong implementation on the inside. I have a slide I can show you how that's implemented. Right now it's not making any noise. Let's see. Okay, so now you can hear it just playing the same note over and over. What this is doing is just randomly selecting a column from the table to play the note. I just happen to make a preset that stored like a kind of a minor, some stuff in a minor scale. Okay, so now this is just randomly selecting from these bars and then playing those, converting to MIDI notes and piping them to the Karplus-Strong synth. There's also kind of a multi-tap, two-tap delay situation going over here with the volume for each of the delay taps. They're synced to the clock. I have a weakness for this effect. So it's just kind of layering successive notes. So yeah, so I think this is kind of gives an idea of what's going on. I don't want to just run this out forever. I'll go through some of my slides. One thing I want to show. So if I jump to panel mode, so basically I pulled out all of the widgets that are actually controlling this performance into the front panel. So this is like Max's presentation mode, sort of like Graph on Parent would be if this was used as subpatch. This would be the display that was shown, but it has the gains and the sequencers for each of the layers for the different instruments. So I can tweak them here, and I can cut them all out, or whatever. So I'll stop this at this point. And so I think maybe this gives a basic idea of what the capabilities are, like how patches look and work, the use of layers to organize the patch, the use of panel mode to kind of pull performance controls together. There's a bunch of other details that I have not touched on, so I'm going to jump into my slides a little bit and maybe talk about some of those. So this was a patch I was going to talk about. Okay, so let's look at this. This is actually the Karplus-Strong synth that I used in that demo. There's sort of 3 display modes being shown here. In the top part, this is the patch editing mode, so all of the elements of the patch are shown. You can navigate between layers. This is like the mode that I was looking at that demo patch in most of the time. And so you can see here, this is just like, all it does is take, it looks for MIDI note on events and converts them to frequencies and then pipes those into this Faust tilde, which is my secret sauce for compiling Faust code and with the LLVM. I'll show you a little bit more about that later. And then there's a couple of controls for the parameters. When I switch this to panel mode, like presentation mode max, the widgets can have a different position in the panel than they do in the normal editing mode. So like down in the lower left here, this is if the CarPlus synth is being used as in the equivalent to a PD abstraction, like being loaded within another patch. It shows panel mode, so that the same two dials are relocated, so they're now like more centrally located there. On the lower right, so this is basically the mode that I was looking at my demo patch in at the end, where it's not being used as a sub patch, or it's not being used as an abstraction, but it's just kind of compressing or compacting the display into panel mode for more of a performance-oriented kind of a vibe. Yeah, so what's next? So you saw this is just some other widgets that this is just a screenshot of some other widgets. On the upper left here, we have a sample player, basically like the ones I was using in the demo, except that the buffer is also piping or it is displaying the waveform in this chart. To communicate between the DSP and the UI, I use shared memory segments, so there's not like a hard the data's not moving back and forth between the UI and the DSP. Over here we have a little scatter plot. This is like plotting an LFO that's being snapshotted every 200 milliseconds in a kind of a rolling data log style. So the x-axis here, I don't know if you can read these numbers, but it's sort of seconds since now. So it scrolls from, as time passes, the waveform scrolls off to the left. And then in the lower left, we have a table widget, which you already saw. So the focus of my paper and what I wanted to talk about was kind of the distinctions between MFP and PD or Max. I think Max, and PD users would be really familiar with what the patches look like, but there's a few things that would jump out, I think. A few of them is you may not have seen this in the demo patch, but to get audio out of the app, you use a processor called out tilde. Why not DAC tilde? This is just a personal pet peeve of mine. I hate the name DAC tilde because it's not a digital to analog converter. It's just a digital audio output. And so I just didn't put it in. And so I called it out tilde instead. PD users would be familiar with pack, like everything has a pack primitive. Why is there only one argument if there are two inlets here? PD user would expect one argument for each inlet. This is both to specify the number of inlets and also to provide default values for them. I never liked that, so I just have one argument, which is the number of inlets. The really important differences, though, are these other ones. Those are just kind of my, because this is my project, I do what I want. The differences in the punctuation here are actually really significant. They look small, but they're really big. So there's a comma here between the arguments of this route car processor. There are quotes around the word channel here, which you would not see in Max or PD. Bang is capitalized. Why? Okay, well, so these are all kind of related together. They're kind of the tip of the iceberg, where the iceberg is called Python data model. All of these items are as strings that you enter into the UI are turned into values by the Python evaluator. So that has a lot of implications throughout MFP. So what we want to talk about here is like what's going on with this iceberg of Python data. So it starts with the TLDR is all message data anywhere in MFP can be Python data of any type. It's not restricted in any way. So that starts with literals in the UI being processed by Python's eval. Plus some special forms. So that means like you have strings here, like literal strings, or in the second example here, string that's produced by evaluating a Python expression. You can have non-numeric, non-string objects like a datetime object that's produced by calling datetime.now. You can have dictionaries. You can have all kinds of other, anything that you can write an expression to generate in Python is a valid message between processors and MFP. There's a couple of special forms that, pause there. So anything in a message box or anything in an argument list of a processor is essentially an initializer, right? It's like it's evaluated at the time that object is created. You could think of them as more like load time constants than like live code, even though like in the second message box, it looks like code. I mean, it is code. It's just executed at the time that you create the message box. If you want to change the evaluation timeline, there's a couple of special forms that do that. So this one with the a comma preceding a form or an expression in a message box is called a deferred evaluation form. So instead of actually evaluating the code at creation time, it just wraps it in a Python lambda and only executes it when the message gets sent over a connection. So in this case, every time you click the message box to send the message, it calls datetime.now, and the message that it sends is actually the current time of day at the time you click the message, rather than in this message box, datetime.now would only reflect the time of day when the message box was created. Similarly, we have messages that start with an @ sign are a special kind of partially applied function where they're typically missing, they're like method calls that are missing a self. And so you send this partially applied function to an object, and then that object uses itself as the self on the method call. So in this case, we're sending a message to this slider, and the MIDI learn method is a method on the slider that's going to tell it to start listening for MIDI events and to set the next CC event that comes in to be a controller for the value of the slider. So then it would just, subsequently you could use your MIDI controller and it would move the slider up and down. So I'm going to skip over this one because I don't want to waste my time. Okay, so the title of this talk promises extensibility with Python and Faust. So I want to talk about a few ways that you can include Python code in your patches. So the easiest way is with Python's Lambda. If we look at this func processor, func is just the thinnest possible wrapper around Lambda in Python. Lambda, if you're not familiar with it, is a way to create an anonymous function in Python that consists of a single expression, and then the return value of the function is the result of that expression. So in this case, we're declaring a function that has two parameters, a and b, and it returns the greater of 0 and their difference. So that's like kind of a clamping type operation. You could totally express this in data flows style, but it's just more compact if you do it algebraically in this case. So func, when this processor is created, actually creates a Python Lambda with that exact code in it, then uses Python's inspect module to determine what the argument signature is, and then it creates one inlet in the processor for each argument. So then it follows normal marshalling rules that PD and Max follow. So it's the leftmost inlet that's hot by default, and the other inlets need to be populated before that. There's another kind of sneaky way to get a Lambda into a patch using this deferred evaluation syntax I talked about earlier. In this case, it creates, I mentioned that it wraps it in a Lambda, so it wraps it in a Lambda that takes no arguments. So you can't parameterize it, but like if you just want to get a Python expression called, you can use deferred evaluation here. So to put it any place you have a message box, and then when you click the message box, it calls that Lambda. So these are pretty basic ways of getting a little bit of Python code into a patch. So also we have this key ability that any Python function is automatically wrapped as a processor type. So if we look at the very top message box here, os.getCWD, so this is just a message box that's calling this function at load time to get the current directory. But this os.path.dir is actually taking the named Python function and creating a new processor for it. So it follows regular marshalling rules, so it doesn't get executed until it gets an input. So in this case, it gets this string input that represents the current working directory, and then it pulls out the directory name portion of it. Similarly, we've wrapped re.sub, so this is the regular expression substitution function from Python, and it has a little bit more complicated marshalling requirements, but similarly to the way we do lambdas, we inspect these functions using Python's inspect to figure out what its argument signature is and create inlets that are that correspond to it. So you can use so basically anything that exists as a Python callable is available for use as a processor, and that actually enables a really cool thing that we can do with live coding of Python processor types. So if we look at the left side here, this processor Straverse, like, it doesn't exist. It's not a MFP built in. It's not a Python built in. It's not a user patch. So when you create this, it'll actually have a little error badge that says, like, I don't know what Straverse is. But every patch element has this custom code property. And we have a little code editor here in the app. This defines Python code that gets evaluated like really early in the creation process of a processor. So in this case, we define a function called Straverse that reverses a string that's its argument. And so once we've evaluated that custom code, then when we try to create the Straverse processor, Straverse does exist. It's a Python function, and so it can be. We have basically a one-off new processor type that we've just live coded in the app. Quickly, I want to talk about how Faust extensions work. I know I'm kind of running out of time.
It depends on how many questions you want.
Yeah.
Like, we still have some time.
So
Do we have questions?
We have, I'll just keep talking.
Okay.
So
Take your time.
For Faust code, we just use the custom code block and provide the Faust code in a Python string. Then it gets passed through the LLVM compilation process. The Faust tilde processor knows to look for this variable Faust code. You can also pass it a file name as a parameter to the processor if you want to load Faust code from a file. But this way you can actually live code it in the app and have it recompile and run again. One last slide I want to show. So this is about embedding MFP. So you can save MFP patches as LV2 plugins and load them in any LV2 host. So this is Ardor. So these two channels have these CAR plus synthesizers each loaded, and then one of them also has this MIDI clock display patch loaded. There's a single instance of MFP that hosts all of the UIs for these. You can see these are all kind of in panel mode, so you can arrange them. And in this window, you can actually see for the first time that the MFP display is it has a tiled workspace manager. So this is tiling these three different patches together. And you can build as many tiles as you want if you want like a big control panel of patches that you've got embedded in your LV2 host. Okay, so I'm going to stop there. MFP is free software. It's available on GitHub. Check it out. Happy to answer questions for as long as I've got.
Thank you for the presentation. Yeah, and do we have, I didn't see, yeah, let's go.
So we heard at the workshop yesterday that there are very few real-time safe scripted languages, and Python is not one of them.
Nope, it's not.
So how do you handle the...
I happen to have a slide for that. I knew that was going to be the first question. It's not. Python's not real-time, so I don't try to force it. So the DSP engine is written in C. There's essentially three processes that are cooperating when MFP is running. The main one is a Python program that runs the message passing network. It does all of the evaluation, and it's kind of the main controller. It's not real-time safe, although Python is pretty performant these days, and there's no UI in that process, so it doesn't have anything else to do. There's a UI process that is also a Python program, and then there's finally a DSP process that's C. They all communicate with RPC and kind of synchronize at block boundaries. So yeah, that's the trick. So we don't, and I can be as real-time safe as I want in the DSP process. It doesn't do any memory allocation. It doesn't do any of the stuff you're not supposed to do in real-time processes. And all of the I/O is handled in a thread that's kind of that's not the UI or not the DSP thread. So I hope that answers your question. Yeah.
So what's your motivation behind adding Petra language to the canon of Petra languages? And don't misunderstand me, I'm not saying that's in any way redundant. I'm coming from the live coding scene, reinventing the wheel is seen as a virtue, and it's a really great thing and a great project. So, but from somebody who has been in the same situation, where did you decide that what's there is not something you want to work with and you want to make your own? And what was your motivation behind it?
Yeah, no, it's fine. I was gonna. You said to me, you know, the first night, like, yeah, everybody, you know, has their own live coding system. And it's kind of true, yeah, but for me, it was like a lot of people come to patching systems as musicians that want to learn how to code, or who are excited about sort of being able to unleash the mad scientist, right? That, and I came to it as a programmer who was like just learning to use software tools to make music. And so I immediately was struck with how data flow languages like are programming languages. They're like, you're writing computer programs. But I was a little bit disappointed in the kind of sparseness of the data types that are available in pure data when I got started. You know, I was wanting to do things that, even simple things that required string manipulation, like became like really painful. It was difficult to do any sort of higher level representations of things like hash tables or whatever. I know, like, I sort of since found out there's plenty of extensions and other projects to do that. But I had this idea of like, oh, hey, if I'm writing computer programs, like, why can't I use the data model from a real language that's like already like complete and really dynamic. So I just been kind of exploring it for, you know, for my own purposes, but also just kind of see what can be done with it. And you know, it's not going to replace anything that's already out there, but I think it's interesting to look at.
Cool, thanks.
Anything else? Like, we have time for one short. Oh, okay. Bitte.
Thank you. Just a quick question about the control computations. So does it, what gets triggered when? Is that like in PD or?
So within the message passing network,
right.
It's very similar to PD. It's sort of depth first, like outputs right to left.
Right. Okay.
Know, that kind of thing.
Yes.
Yeah. It's just so it's at least predictable. Yeah. So basically,
maybe because this was a really quick one. The next quick one: how do you navigate the levels? The different patches, the different. So how did you call them?
Layers.
Layers.
Oh,
right.
Yeah. So there's key bindings for everything, so you can use page up and page down, like to go through the layers, you should be able to. Let's see what's the problem here. Page up, oh, my shift lock on. No? Yeah, there's my my app may have locked up at some point. I'm not sure what's going on with it. Yeah, it's not okay. It's crashed. Luckily, it made it through the demo. But yeah, page up, page down to navigate through the layers, or there's a menu that shows them all. Essentially, I wanted there to be keyboard equivalents for literally everything. I wanted to be able to run the app without touching the mouse at all, including things like connecting elements together. So like it's a very modal UI that's like, for example, to connect. Like if you have an element selected, you type C to enter connection mode. Then you can hit like tab to jump to the next element, and it will automatically, you know, sort of pencil in a connection to inlet 0, but then you can use number keys to switch to a different inlet for the connection destination and so on. So you can make all these connections without actually ever touching the mouse.
Okay, yeah, thank you. And yeah, so we're moving on to the last paper of this session. PD Lua, Signals and Graphics, and it's presented by Timothy Schön and Benjamin Wesch.
Use that one, or would you prefer this microphone or the big one? No, I think it's fine. We have hand one.
Sometimes you just gotta mess around a little bit.
There you go with macOS.
Yeah, I was about to say this is our fault for not using Linux.
This is the curse. But it's supposed to be full HD also. I mean, it's okay. Why so ever? So now it's just. That looks right. Okay, so first of all, thanks for the invitation. It's an honor to talk here, surrounded by so many famous audio programmers, and myself not even coming from a programming background. So I also want to thank Albert for inviting the two of us to contributing to this paper. Maybe a very short information on my background. I'm studying in Linz at the Tangible Music Lab, and I'm mainly into creating audio. And I found PD like 4 or 5 years ago, and then I started to look a bit more into it. Like, it's open source, you can see anything that's going on. And now trying to contribute a bit to that. I mean, I still have a lot to learn, but this PD Lua contribution, my part is actually very small, is also a result of that. And I don't know, Tim, if you want to talk a bit about.
I'm Timothy Schoen. I studied music technology in Utrecht, where I started developing Plug Data, which is a new spin-off of Pure Data. And from there on, I got involved with the PD Lua project, which is what we're going to be talking about today.
Great. So we're starting with something that's probably not really necessary. I mean, there were so many talks about Pure Data. Everyone probably in this room is familiar with Pure Data. I wasn't, as I told you, until a few years ago, and it's funny to see this quote from 28 years ago. I thought I might present the graph here of the contribution, so it's very much alive. The next version is upcoming in the next few years, and one really radical change there is that you will be able, after 28 years, to change the colors in vanilla. That's but I'm not involved in that, so I'm just happy about it. Yeah, so the background, because we want to lead to PD Lua, obviously. External development, when you want compiled objects, for someone like me not coming from that background, is a rather complicated thing. It's possible, but you obviously need to know your ways around C or C++ or whatever you decide to use. And yeah, Pure Data doesn't have any integrated scripting options like, for example, Gen or Gen Codebox or JavaScript options in Macs. And that's where we can switch the topic to Lua. I mean, there was a really nice talk about Lua already by, now I forgot the name. Robin, yes, Robin. I mean, he summarized probably the major parts of Lua already, but we have a slide for that as well.
Yeah, so Lua probably doesn't need that much of an introduction, but Lua was started in 1993 in Brazil. It basically distinguishes itself by being a very efficient and fast scripting language, and also being very easy to embed into basically any kind of application, which is why it's very popular in game development nowadays, specifically for the development of mods. And since externals are basically just mods for pure data, it also lends itself very well for the development of externals in PD.
So about PD Lua, I have a tiny snippet of a video prepared for that. I talked to the guy, he's fine with me showing it. It's Ewan Bristow. He's a quite young plug data user doing really some incredible stuff in plugin development. And he did a live session, I think, a few weeks ago. He's sharing what he's doing, and I mean, it's a younger generation, like sharing with the chat and getting feedback during the stream. It's really worth a look also. I mean, maybe not 3.5 hours, but it's cool. And he got a question about PD Lua. Currently, he's mainly using vanilla options. And there was this snippet that I found really nice. Wait a second. I think, no, it should be fine. Yeah. So you should get signal, right? Okay.
Do some Googling with PD Lua, because you can do some extensions. I think PD Lua is in, you can open stuff up in Plug. You can open up a Lua editor. Oh, whoa, I haven't checked this out. Damn, hello, what's this?
So, this is the question that we want to answer, right? It's a bit funny because the PD Lua object itself like exposes the Lua code of the PD Lua plugin, so it might be confusing for users if they think they can use the regular option to open the object and edit the Lua code. In this case, it's not intended like that. Anyway, PD Lua has quite a long history as well, starting from 2007. I admit I don't even know how to pronounce probably the name of Claude Hyland Ellen, whatever. Oh yeah, then it was probably fine. And so, and it changed maintainers a lot, and now it ended up, for now, since a few years, probably quite a few years with Albert. And now it got a bit more of an impulse in further development through Timothy's great project, Plug Data. So it's an external that lets you obviously develop your own objects in Lua language. And the original version that's been around for a while mainly was for control processing. So it didn't have, exclusively. So it didn't have any options for graphical objects, and it didn't have any option for sound input or output, and obviously then also manipulation. That's where Tim can talk a bit more.
Yeah, so I came into this because I developed Plug Data starting in 2021. The idea was to basically create a new pure data flavor that would focus on being able to run inside any DAW. So we have plugins available in VST3, LP2, CLAP, and audio unit formats. Obviously runs on Linux, Windows, Mac OS, and a whole bunch of others, FreeBSD, iOS. And another thing that I try to focus on a lot is to provide a bit more of a modern user interface experience, because PD was made in the 90s, and you can sort of see that a little bit. So if you're familiar with Macs and you're looking for something open source, definitely check it out. Albert proposed that we should include PD Lua into Plug Data in 2023, which I thought was a really good idea, because it basically provides a really easy way to write externals without needing to know C code. And one thing I kind of ran into after a little while was that there was no real way to create custom graphical objects for Plug Data. Pure Data actually has a C API for that, but plug data doesn't. And even the C API that is provided for pure data is pretty complicated and not really something that normal users would want to interact with. So I kind of saw an opportunity there that if we could create graphical objects using PDLUA, that would both greatly benefit both projects, basically. Yeah, and when we started adding graphics, as you will see, we also ran into some other things where we thought we could extend PDLUA a little bit. And the first one was audio signals. So as previously discussed, PDLUA initially could only deal with control data and not with audio signals. So that was something that we definitely needed to address. There's another project called Ophelia that also provides Lua functionalities in PD, and they already tackled that. They could already do audio. So basically, I just stole their API and included it in PD Lua. And you can see here basically how it works. You define inlets and outlets as signal, signal, signal here. If you, instead of signal, say data, you create a data inlet. And that signature has to match with the perform function. So you see we have two arrays of samples that we take as input. And we return one array of samples as output. If you've worked with audio software, this will look pretty familiar, I think. But you can just loop over the samples, fill a new buffer, and then return that buffer in order to output it. There's also a DSP function, which informs you of the sample rate and the block size that PD expects to use.
That's where I come in again. I was a lot working and experimenting with spatial audio and PD, since I don't know exactly, I don't remember exactly when, but it has this multi-channel optionality with the snake objects and support in many of the standard objects also. There will be a lot more with the next version now. And I thought it might be nice if PDLUA also provided that option. I mean, in the beginning, I thought it's mainly cosmetic that you don't have all these connections, but that's a big advantage. And also with some stuff coming up, the snake or the multi-channel cords really make sense and make things easier. So we decided that we could add this here. So now with the multi-channel support, you also got with the DSP function channel count argument, and you got the option to define the output channel count. With a method that's also taken from pure data itself. It's also the same name. And then you can work with the input where each channel just has channel count times block size samples that you can work with, and the same is expected for the output. So very simple way to work with multi-channel. Yeah.
So now to the main event, graphics. The way this works is I try to implement this as the most normal kind of standard vector graphics kind of API. If you've worked with something like Juice before, this will look very familiar. So first, obviously, we need some kind of function to change the size of the object, because if you create something graphical, you need to set the bounds for it. So that's where the set size function comes in. And then you have a paint callback where you do the actual painting of the object. And you can see here, we set the color, first the background color, then we call fill all to fill the whole rectangle. Then we fill and set the color again to something else, and we fill an ellipse. This is pretty normal vector graphics stuff. So this is callback-based rendering, where you define a paint function that gets called whenever a repaint needs to happen. If you want to trigger the update manually, you call repaint. Sometimes the program itself will decide, oh, like the window shows or hides, and we need to call the repaint. So that's why this is a very useful way to do it. Other things we can do is translate, scale, draw text, fill stroke ellipses and rectangles. We can define paths and curves with cubic and quadratic curves, and fill and stroke those as well. So this is a pretty complete vector graphics implementation that you can use both in pure data, plug data, and per data. Another small little detail is multi-layer graphics. So sometimes you want to draw something different on the foreground and background. And when something on the foreground changes, you don't want to like redo everything that you've drawn. So you can define multiple layers that you want to repaint individually. If you define a function called paint layer 1 and paint layer 2, you can call repaint 1 and repaint 2 to repaint them individually. It can save you some CPU cycles if you're drawing a lot of stuff. And finally, if you have an object with graphics, next thing you want, obviously, is mouse interaction. So we also have mouse down, mouse drag, mouse up, and mouse move functions. This also looks very familiar if you know processing or if you know juice or something like that. This is pretty standard fare. And now it's time for a live demo.
So yeah, first thing I wanted to show, since Tim decided for Plug Data to really have also some optimized drawing. Now I have to find the right window again. Where did I put that? Ah, here. Yeah, it's very fast, the drawing with Plug Data. So what you can do with Plug Data, you cannot do the same way in Pure Data. And I just prepared a little patch with a PDLua script running, where you can see that it's quite performant here. So it's a text with lots of characters, and they're all interacting here. So for the drawing, shaders are involved, but obviously the calculation is all done in Lua, and it's pretty fast. And if you want to edit this now, in Plug Data you even have a code editor integrated. So let's just maybe change a bit here. It also supports transparency on the Plug Data side. Make the characters bigger. And yeah, so I mean, this is not necessarily the intended use that you do visuals with Plug Data, but it's possible so far for this demo. And the next thing I want to show would be actual use in PD Vanilla. So we didn't even talk about that yet. If you want to install, I have to remember now, the find external options is changed menus with the new PD version. So here in 55 it's still here, but 56 it's going to be its own tools menu. PDLua is also on Decken now, so it's very easy to install. You will find it here. You see all these uploads by Albert. Oh, one that we might get rid of by me. It's because I started with this automatic upload process to make it a bit easier for Albert. Okay, maybe you can hold the microphone because then I have both.
Of course, makes sense.
So, yeah, sorry. It's two objects that I need to show, or wanted to show you. Ah, perfect. The one thing that I'm constantly using as an object is, let's just quickly do it this way, is a show object. I was always missing some kind of inspector where you can easily see the signal and also look a bit further into it. We don't have any output, so it should be fine. Yeah, so you see this is a PDLua object. It also allows to resize. You can zoom in, you can zoom out. I mean, with noise, it's not doesn't make that much sense now. So the next thing I want to show here, and I use n and tilde. It's not connected to this talk, but it's easy to create some interesting timbres in that way. It's an object that I created for playing around with a controller. And it's exactly for this use case where other people are watching and they can't see what I'm doing with my fingers. So I thought when I'm demoing stuff, it might be nice if other people could see what I'm doing and understanding the interactions. And for that, I created this object. I mean, this looks a bit untypical in PD Vanilla. People are not used to seeing stuff like this. So what was it called? well, wait, give me a second. I need to check myself what the stuff is called. Exactly. So this thing will then also display the movements. Not like this, just a second. Yeah, so I even get the movements, everything, and it's better to understand what's going on then. And it looks nicer in Plug Data. Yeah, actually, let's quickly open it because Plug Data's rendering is more beautiful with the anti-aliasing there. So if you do the same here, yeah, I mean this is fancy because you have really smooth lines. But I'm happy. I'm still a vanilla user, I have to admit, even if Tim is right next to me. So, and yeah, now what I can do, of course, is let's get the acceleration here. I'm just giving you a bit of an impression when I'm working with this stuff, so not this one. I want the other show. Creating an audio signal from the acceleration data and then showing this, and then I have an option to see this, and then if I zoom out a bit, it's quite comfortable to have the option to understand that stuff and not have the need to always create some areas or so to write into. Oh,
we got a glitch going on.
And we have a glitch going on. Let's just reload, then it's probably fine. Okay, yeah, well, the idea was just that I might now use this and make something audible also. Come on. Looks like there's something going on, but of course that's another use case to also check what signal am I getting here. And now this should change when I move the controller. So if we make this audible now, and let's check if PD has the right output. No, it doesn't, but now it has. So take care. Then it's a bit of a performance now. Okay. Yeah, but I mainly wanted to just demonstrate this inspection tool that I really tend to use almost in every PD session now, and this is only thanks to PD Lua. I mean, of course, there's plenty of stuff. What we did not show here, or what I did not show here now, is you could obviously also generate signal. For me personally, that's currently not as relevant because that's why I learned pure data, but there might be some interesting use cases for that. So you saw it's very easy to install. Feel free to play around with it, and we have an active maintainer, so whenever there's any requirements. Okay. So this was the live demo part, I assume. And then future work, Timothy M.
So there's still some things that we're currently working on. One is support for just drawing SVG from files, or from text actually, I should say. So this is sort of the example SVG demo Tiger. There's going to be some limitations to that because SVG also has pixel-based effects like drop shadows, and that's probably a little bit outside of the scope. But yeah, so SVG drawing is one that's going to be added. Mouse interaction needs to have mouse enter-exit functions, preferably. Charles Nymock is working on support for properties menus. So you can actually, in PD, if you right-click on like a user interface object, you can open properties and you can change things. So it would be really nice if you could also do that for Lua objects. We're gonna add options for text alignment, so you could align left, right, center, which is easier than calculating it out yourself. And obviously, a little bit more documentation is always welcome. But Albert has done a good job of that already, which you see here. So the PD Lua intro, if you're gonna start working with this, I highly recommend checking this out, because this really explains almost everything you need to know. Yeah. Too many tabs. What's in the other? Yeah, and of course there's the help patch that's included, and there are examples that ship with the distribution. And one thing I wanted to mention, I'm not sure if I forgot, but this also works in PurData, and I think it's a work in progress somewhat for Web PDLorc and PDLorc, so it should at some point arrive there too, hopefully. He's right there. Yeah, I talked to him about it actually. And so that would basically make it the first kind of cross-PD flavor solution for drawing graphics. That is also easier to learn than most available options out there right now. That was all.
Okay, thank you. Do we have questions? Then I will just, now I didn't forget.
So is it the same object that does both control and signal data? It's coming from the same PD Lua object? So there's no like PD Lua tilde variant or something like that?
Good question. There isn't. There's the PD Lua object itself is primarily so you can access the help file, because what actually happens is you put a .pdlua file in your search path, and that becomes the actual object. So pdlua is more of an object loader that finds the files, and in that regard, there's no difference between signal and data, indeed. Yeah.
Does it have any kind of time abstraction? Like, could you easily do a sequencer in PDLua or something? Or how would that work?
So there is a timer object inside PDLua, so you can indeed do timing. Of course, you could also create an inlet and just use a metro object in PD to do timing.
Okay.
So that's always possible. But yeah, that is indeed very much a thing you can do. All right. Thanks for listening, everyone.
Thank you.
Thank you, Henrik. Thank you, people, for presenting during the session. Before you're allowed to drink coffee, we are all going to go outside in the sun so that we can take a picture, which Nando is going to take. Thank you, Nando. So we all meet outside of the venue, and once the picture is taken, then you can go get a coffee. See you outside.